Hello everyone. I again welcome all of you in the fourth lecture of this drawing and storage engineering course. So before we start before we start the today's class, so I'd like to revise the previous topics, yes, which we discussed already. So as we know that first we had a discussion on this moisture content, how the importance, how the moisture content benefits or help the drying process, or how the removal of moisture helps to store the product for a long time. Then we have seen that there is two main way of representation for moisture content. One is dry basis, another one is wet basis moisture. In dry basis moisture, we had seen that the mass of moisture divided by mass of solid present in product, but in wet basis moisture, mass of moisture divided by mass of product. And then this WB or DB, both the values can be represented in percentage decimal or in percentage, in decimal or in percentage, yes. And then there are mainly two methods, two methods to determine the moisture content of product. One is direct method, another one is indirect method. Then in direct method we have seen that by air oven methods are there, vacuum oven methods, then Brown Duvel fractional distillation method. Another one is then infrared method. And in indirect method there are you remember electrical resistance method, dielectric constant method. Then you have the chemical method, chemical analysis. So these are the methods are there to determine moisture content. But all the cases we must continue the drying process until and unless the two consecutive weighing of product become same. If the two consecutive weigh of product become same, that means the drying has accomplished. So now next we have seen that equilibrium moisture content. So equilibrium moisture content is the it says nothing but the moisture content of the product after once it gains or loses moisture from environment or to environment due to the vapor pressure gradient between atmosphere and product. And this moisture content, after equilibrating, the moisture content of the product is known as, yes, equilibrium moisture content. And this phenomena of gaining or losing moisture is called as hygroscopicity. And this losing or gaining moisture we can plot in the graph between equilibrium moisture versus equilibrium relative humidity, and that graph is called as Jobson isotherm. So that Jobson isotherm is a S-shaped curve. And then we have seen that the equilibrium, if the product gains moisture, then it's called, if the product gains moisture and then we plot this, between equilibrium moisture versus equilibrium relative humidity, then it is called as adsorption isotherm. Another one is called as desorption isotherm, reverse one. So the difference between this desorption and adsorption isotherm at same relative humidity, yes, very true, at same relative humidity, the difference between adsorption and desorption isotherm is called as hysteresis effect. And then we have a determination of equilibrium moisture content. We have seen static method are there, dynamic methods are there. And then in dynamic method we have seen isotonoscopic method is there. Then static method we have seen acids, or by using acids or salts we use determine the equilibrium moisture content. And then yes, we have we had a discussion on equilibrium moisture content models. We had several numbers of models available, but out of these Henderson equations are the most popular. 1 minus RH equals to, yes, tell me, exponential of minus C into T into RE to the power N, where this C and N both are constant, depends on temperature. RH is relative humidity, depends on when decimal value, and Me is equilibrium moisture content in percentage dB. And then we have seen different drying rates, constant drying rate, falling drying rate. So out of this constant drying rate, we know that if the product surface is saturated, then it's fallen under constant drying rate. Moisture will be evaporated from the surface continuously without any disturbance. But if the surface is not saturated or unsaturated becomes, if it becomes, then the moisture migration occurs from center to the surface. So if the moisture migration from center to surface is more than moisture evaporation from surface to environment, then it is fallen under second falling rate. And if the moisture migration from center to surface is less than moisture evaporation from surface to environment, then it is fallen under first falling rate. And then we have we have seen different types of moisture: bound moisture, free moisture, unbound moisture, equilibrium moisture. So ultimately we discussed about all this. We have a discussion. We know that the formula of constant drying time, the formula is m0 minus mc by rc, whereas the falling drying time, mc by rc ln of mc by m. Both the values of moisture content will be in decimal and in dB, and rc is constant drying rate in mass of moisture by mass of solid per second. So up to this we discussed. Now going forward, let's begin our next today's class. So here you can see the formulas. The formula of moisture ratio is given. MR moisture ratio, it's nothing but m minus me by m0 minus me, where this m is the final moisture after T time of drying, and me is the equilibrium moisture content, and both the values will be in, all the values will be in decimal and in dry basis, and m0 is the initial moisture content. For unsteady state drying, derivations we have performed here. So what we can do here, dm by m minus me, this is the variance of moisture. It's proportional to time, but as along with time the moisture content reduces, so we have given the minus sign here. Now next line we can write dm by m minus me equals to minus k into dt. One constant we have taken, k is the constant, that is called drying rate constant, and the unit of this drying rate constant will be per unit second, or we can say second inverse. Next we have, in the next line we have integrated from initial moisture to final moisture. So initial moisture is m0, and the final moisture after T time of drying is m. So if in the left hand side, if we integrate, then it will be initial m0, final m. So m0 to m, function is dm by m minus me equals to minus k is the constant, so I have taken it out, and in the integration from 0 to T time, so it is dt. Next, if we integrate, then it becomes ln of m minus me. Okay, so ln of m minus me, and the limit value from m0 to m equals to minus k into t. And then in the next line, the value we have to put, the value of m we have to put once m, and the next time we have to put m0, because limit. So ln of m minus me minus ln of m0 minus me equals to minus kt. And then the formula of ln of a minus ln of b, we know it's ln of a by b. So that's why we can write in the next line ln of m minus me divided by m0 minus me. So then equals to minus kt, and then left hand side ln is there, so that ln, if we take in the right hand side, it becomes exponential. So finally we get m minus me divided by m0 minus me equals to exponential of minus kt, or m minus me by m0 minus me we can write as moisture ratio. So moisture ratio equals to exponential of minus kt. This is a formula of unsteady state drying. Next, you see the movement of moisture inside the porous product. So there are several number of movements occurred, during drying inside the product, because the product, I told you that this product, there are solid matters are there, moisture is there, pore spaces are there. So through the pore space, the moisture migrates from center to surface, from surface to surroundings. So the movement of the moisture is not linear. Okay, so the movement of moisture is totally non-linear or zigzag. So this happened due to several number of forces. So according to that, we can classify here. Number one, capillary flow due to surface force, and liquid diffusion due to moisture difference, surface diffusion due to moisture diffusion in pore, and then vapor diffusion due to difference in vapor pressure, thermal diffusion due to difference in vapor temperature, and hydrodynamic flow, that is due to liquid and vapor movement. So this is about the movement of moisture inside the product. Next, you see these graphs already I discussed in our previous classes. So you see drying rate versus moisture content. So from A to B there is initial adjustment, and then from B to C there is constant drying rate. That is because if the surface is fully saturated, and now the surface is not saturated, so that's why it reaches to critical moisture content, and after this critical moisture content, falling rate starts. And that falling rate also, it can be divided into two: first falling rate and second falling rate. Same way I can express the graph into moisture content versus time. So here also from A to B adjustment, from B to C constant drying rate, linear, and then from C to E, that is, it can be divided into two: first falling rate and second falling rate. So here you can see several graphs are plotted between drying rate versus time, but these graphs are plotted but depending on several numbers of factors. So here you can see the thickness of product. If the thickness of product varies, then how the drying rate change. So depending on this, we can elaborate this drying rate process. Next, there are different heat transfer way is there, methods are there. One is first latent heat. That latent heat means, I know it's nothing but the phase change, and phase change means it's moisture to water vapor into air. So that is my latent heat due to evaporation. Then happens sensible heat, that is due to conduction. And then there is sensible heat due to radiation, and then there is sensible heat due to convection. So these are the possible way of heat transfer that occurs during rain drying. So one diagram you can see, one kernel we have plotted one kernel or maybe one product. So from ground there is conduction, then from atmosphere there is convection and radiation, and then from product to atmosphere the moisture content is evaporated into air in water vapor. So as water vapor, so due to that latent heat, so if we express this whole process into an equation, then the equation looks like this: Kc into Hs minus H into Hfg equals to Hc into T minus Ts plus Hr into Tr minus Ts plus U into T naught minus Ts. So you see the left hand side, the term is called latent heat. So that latent heat Hfg we can write in as the latent heat, and then the right hand side, the first component, which is nothing but the sensible heat due to conduction. Then second component is sensible heat due to radiation, and the third component is sensible heat due to convection. Next, there are types of airflow. So these types of airflow in drying, so depends on the types of airflow we can classify the drying process. There are mainly three classifications. One is co-current, counter-current and cross flow. So this by name already you can picturize it. Cross flow means the grain and the drying air, both two will be passed in 90 degree. Okay, in 90 degree they will pass. So there are mainly three types of airflow which occur during drying process. Cross flow. In cross flow, products and air is met at 90 degree, needs mixing of grain uniformly. Hot air meets grain layer and particular side of grain is heated but the other side remains cool. So here one diagram is given, grain flow and air flow, both the grain flow and air flow passing in 90 degree angle, and we have plotted one graph between moisture content versus time. So this moisture content at A sections, you can see in the diagram, it will be very high. Okay, because along with time the A section moisture content can't be reduced, whereas the moisture content at B section will be reduced very high rate. So this is the difference occurs. At same time, grain and air temperature, both these two, if we plot against distance, then you see the grain temperature will vary but the air temperature doesn't vary. The air temperature remains constant and the grain temperature at A section will be closer to air temperature, whereas the grain temperature at B section will not be closer to air temperature, and the mean grain temperature will be just constant. Okay. Next airflow in drying is co-current flow. So in co-current flow, you know already that the heated air and the grain both will flow in same direction or opposite direction. Tell me. Yes, it will flow in same direction. So you can see here, heated air and grain are parallel to each other. Hot air is first made non-heated grain, and then there is restriction of elevation of grain temperature to level of drying air. So you see the grain flow and the air flow both occurs in same direction, and the air flow first, that is the heated air, and the grain that is non-heated grain, that both will comes together. So that's why in co-current flow there is a damage, there is a possible chance of damage to the quality of the grain. So we mostly prefer counter current drying. So you can see the moisture content versus time graph is plotted. Now most obviously moisture content will be gradually decreasing, and the grain temperature, air temperature also it is plotted. You see the air temperature it is decreasing, and grain temperature also it will increase first and then it will start to decrease. It will be close to air temperature. Next, there are the last counter current flow. So this counter current flow means here heated air and the grain both will flow opposite to each other. So here heated air first meets the heated grain and then drying is almost completed. Means in this case you see in the diagram the grain and the air is coming from opposite side. So hot air is directly not coming into contact with grain. Hot air is coming into contact with that grain which is coming out of drying chamber, means which is already heated by hot air. So that's why the damage to the product is not so much. So that's why counter current is also very much preferable during drying process. And you see here moisture content versus time we have plotted. So it's decreasing, and the grain and air temperature we have plotted against distance. So here the air temperature it is increasing as the time goes, but the grain temperature it will be also increasing, but it will close to the air temperature. So now here I would like to finish the today's lecture. Before I finish this class, I'd like to revise the previous, I'd like to revise the topics which we discussed today. So today we discussed about that unsteady state drying. In unsteady state drying, we have seen the moisture ratio. Moisture ratio is M minus Me by M naught minus Me, where this M is final moisture, Me is equilibrium moisture, M naught is initial moisture, and all the moisture contents are in decimal and in dry basis. Next, we have seen this unsteady state drying. The formula of moisture ratio is exponential of minus Kt, where this K is called as drying rate constant, and the value of drying rate constant is given in per second or second inverse, and T is the drying time. And then we discussed about we have seen different drying curves, like the drying rate versus moisture content, drying rate versus time, those things we have seen. We have elaborated some elaborated topics, how this drying rate changes based on thickness of product or based on the time of drying. Okay, then we have seen there are different types of airflow that occurs during drying. One is cross flow, one is counter flow, one is co-current. So in co-current, the grain and air both meets at same direction, and in this case the hot air directly meets with the cool grain. Means in this case the cool grain comes into contact with hot air. So at this, because of this reason, the damage to the quality of product occurs. So in counter current, the hot air and the cool grain comes from opposite direction. So that's why hot air is not directly coming into contact with the cool grain, because the cool grain enters from the opposite direction, and while the hot air is coming out of the drying chamber, at that time hot air also is losing temperature or losing the energy. So that's why the damage to the quality of product is much less. And in cross flow of drying, we have seen the drying air and the product both meets at perpendicular or at 90 degree. So today's class